Good afternoon, and welcome to the latest installment of Goddard's Engage series, and a very special welcome to those employees from other NASA centers who are joining us today as well. My name is Laura Bleacher, and I'm from Goddard's Office of Communications. We are thrilled to have two members of the OSIRIS-REx team with us today to tell us more about the mission and the historic event planned for tomorrow, the first sample collection from an asteroid surface by NASA. During touch and go, or TAG, the spacecraft will maneuver down to Bennu's rugged surface to collect a sample for return to Earth in 2023. Before we get started with today's presentations, I have a little bit of housekeeping to cover. We'll hold questions and answers until both of today's presenters have had a chance to speak. We collected a few questions already using the question tool in the advertisements for this event, but you may also use the chat box to ask a question. If you don't see the chat box, you may want to try opening this Ustream link in a different browser. And please note that this session is being recorded and will be made available for later viewing at the same Ustream link. And now it's my pleasure to introduce our two speakers. First, we'll hear from Dr. Lucy Lim. Dr. Lim is the Assistant Project Scientist for OSIRIS-REx and a research scientist in Goddard's Solar System Exploration Division. Before joining OSIRIS-REx, Dr. Lim studied asteroids on the Near-Earth Asteroid Rendezvous, or NEAR mission, as well as leading observation programs using the Spitzer Space Telescope and various ground-based observatories. Dr. Lim received her PhD in astronomy from Cornell University and a Bachelor of Science in Earth, Atmospheric, and Planetary Science from the Massachusetts Institute of Technology. And then after Dr. Lim, we'll hear from Dr. Benjamin Ashman, who is the OSIRIS-REx Independent Verification and Validation Navigation Team Lead and the Deputy Position, Navigation, and Timing, or PNT, Policy Lead at Goddard. He began work at Goddard while a graduate student at Purdue University, where he received his PhD in Electrical Engineering in 2016 and a Bachelor of Science in Electrical Engineering from Ohio University in 2010. So I'm sure, like me, you are looking forward to a couple of great presentations and learning more about this amazing event tomorrow. And so with that, I will turn it over to Dr. Lim. Thank you.
Thanks so much, Laura. So tomorrow is the big day for OSIRIS-REx. We're going to send our spacecraft to the surface of Bennu and grab our asteroid sample. And this will be NASA's first surface sample return since Apollo. There have been a couple other sample returns from NASA, notably the Stardust and Genesis missions, which were flying the sample collector through space and collecting particles this way. But this is the first time that we're going to send a spacecraft to the surface of a solar system body and grab a sample in quite a long time. Thanks everyone for tuning in. Tomorrow's the big day. Next slide, slide 1, I think. All right, so what I'm going to talk about, like why are we going to Bennu, and a little bit about where we think Bennu came from and what we're going to learn, what we've been learning and what we're going to learn from it, some surprises that Bennu had for us once we arrived there, and then a little bit about the sample site where the spacecraft is going tomorrow. And in the next talk, my colleague Ben will get a little more into the nuts and bolts about how we're getting the spacecraft to do all of these things and grab our sample. So slide 2, please. Okay, so asteroids. Many of you may remember that most of asteroids in the solar system are orbiting between Mars and Jupiter on stable orbits where they can just live there for 4 billion years, and most of the time they're just going to stay there and nothing is going to bother them, most of the time. And studying asteroids is great because they're leftovers from the very early stages of the solar system. So you won't find any rocks on the Earth or even on the Moon that go back to kind of before the formation of the Earth and Moon, because as over the history of those two bodies, the Earth is really good at recycling rocks. Like every rock that went into the formation of the Earth has been recycled mostly, usually a bunch of times since then, like broken down and recycled back in the mantle and re-erupted as a lava somewhere, and then, and eroded away back down. There's nothing on the Earth that really goes back to the very early solar system. And even on the Moon, where the rocks are a lot older, everything on the moon is pretty much an igneous rock. Like they've all experienced a lot of melting and a lot of processing since the time that the moon accreted as as a body. But asteroids are just enough smaller that they don't have most asteroids don't have like the melting and recrystallising process going on. And so when we look at rocks from asteroids, we really can see things that accreted in the solar nebula 4.5 billion years ago, and they're still there, and we can still study them and understand the conditions that that the building blocks of planets formed in way much further back in time. So most asteroids, including Bennu, spend most of their time in the main belt where the orbits are stable. And this is so this slide here is very kind of cartoon drawing, showing the position of the asteroid belt. But if we go to slide 3, we can look at the asteroid belt in a somewhat more mathematical way. So this is a plot of where all our asteroids are. Each little blue dot is an asteroid. And on the x-axis, we have semi-major axis, the distance from the sun. And on the y-axis, we have the orbital inclination, like the tilt of that asteroid's orbit. So you can see that there's a lot of structure in the main asteroid belt here. And all these white stripes where you don't see any asteroids, there's a reason for that. Those are real. They're not like an artifact of data processing or poor image quality or anything like that. Those are resonances, orbital resonances with Jupiter and Saturn. And that is where you cannot orbit for 4 billion years and just stay there, because you'll be kicked out of that orbit pretty quickly compared to the life of the solar system. So an asteroid that finds itself into one of those resonances, it's like they're falling through a trap door right out of the main belt. And oftentimes that means into the inner solar system. So that's how near-Earth objects kind of happen. And usually that's precipitated by an event in the asteroid belt, such as a collision. So there will be a collision will happen in the main belt, and the pieces of that collision will then be moving slowly in one direction or another, and they'll be pushed in one direction or another in semi-major axis by oftentimes by non-gravitational forces. So there's a particular effect called the Yarkovsky effect, which basically comes from the asymmetry between the thermal emission on the morning versus the afternoon side of the asteroid. And that's a really tiny force compared to gravity, but over thousands to millions of years, it can actually become really important, especially for smaller asteroids. So because of these Yarkovsky forces, once you produce small collisional fragments in the asteroid belt, a lot of them will end up in hitting one of these resonances and falling through that trap door into near-Earth space. And next slide. So this on slide 4, you can see some of the results of that. So at first, they'll end up with their apoapsis still in the asteroid belt and their periapsis in the inner solar system, and then further encounters with the inner planets can kind of circularize those orbits. And once this happens, as you can imagine, like they're not going to last for 4 billion years anymore. The lifetime after getting ejected from the main asteroid belt is on average probably less than 10 million years or so. So that's why we think that Bennu, which is a near-Earth asteroid right now, probably almost certainly spent most of its lifetime in the main asteroid belt and is a relatively recent arrival into near-Earth space. So what happens to them, like either they collide with something, oftentimes it's actually with the sun, but sometimes it's a planet, or they'll have an encounter with a planet or the sun that will eject them straight out of the solar system. So slide 5 shows you a little bit of the history of exploration of near-Earth objects. So we have been to near-Earth objects before with our robotic space missions. So what's special about Bennu? Like, why do we need to also go to Bennu after doing this? So on the left, some of you may remember the NEAR mission, our first asteroid orbiter, which turned into our first asteroid lander, which visited an asteroid called 433 Eros. And on the right, this was the first ever asteroid sample return mission, which was done by the Japanese space agency, JAXA. And the name of this mission was Hayabusa, and it brought a tiny, like milligram-sized sample back, but extremely scientifically important, from this asteroid known as Itokawa. And these are not to scale. Like, you know, Itokawa is about 60 times smaller in length compared to Eros. But they look very similar to each other in certain, you know, in terms of their material properties, and not very similar to Bennu. And we can kind of see that in context in slide 6. So as it turns out, asteroids are not all made out of the same thing. And so Itokawa is on the slide, but it's very small. It's hard to see, but it's about the same color and brightness as Eros, which is down kind of below the center, just right at the center of this slide, or Gaspra, which is in the top left, or Ida, which is in the top right. Like, all those three asteroids are extremely similar to each other. In terms of color and brightness, they all reflect about 25% of the light they receive from the sun. And more importantly, in their visible and infrared spectra, we can see that they're very similar to each other. They have the same spectral features, telling us about the same minerals on each of those asteroids. And because of the Itokawa samples, we know we have ground truth for that as well. And we know that those asteroids are made of things that did condense from the solar nebula, but they experienced some high temperatures in their past. And so they're pretty dry. They didn't interact with a lot of water on the way, and they're mostly kind of high temperature minerals. So contrast that with Bennu, which is also too small to see on that chart. So I'm going to point you towards 253 Matilda, which is in the bottom, the very large asteroid in the bottom right of the chart. That's the color of Bennu. And between the color and the low albedo and the spectra of Bennu and Matilda, we think that when we're looking at them, we're looking at something a little bit different. So slide 7, we'll explore that in a little more detail. So those are probably related to some materials that we've seen in our meteorite collection as well. So instead of accreting kind of anhydrously, like the material from Itokawa, which is what we get most of the time when we get a meteorite, we get a few meteorites that are water rich. And when we say water rich, the water is locked inside the minerals. Like we have minerals that have reacted with water and incorporated that water in their structure. And most of the time, that also comes with a variety and complexity of organic molecules, carbonaceous compounds, and so, occasionally other carbonaceous compounds such as carbonates as well. And so that this water and carbon rich composition, we think it's actually very widespread in the asteroid belt. It's probably even the majority of material there, but it's just not the majority of material in near Earth space. So it's extremely important in the early solar system, and we definitely want to get a sample of it. So slide 8 shows us what we knew about Bennu. So everything we knew about Bennu before launch told us that not only was it going to be accessible, but it was going to be, kind of that carbonaceous chondrite-like, Matilda-like type material. And here you can see the fantastic sheet model that we got in advance of it from the radar data that we had from the Arecibo and Goldstone radio telescopes before this mission was even planned. And you can see that that we had estimates for the density being much lower than the density of Itokawa or Eros, and the albedo being only 4% instead of 25%. So it's, Bennu, we say it's dark like a lump of coal. And the spectral type also gave us confidence that there would be carbonaceous material there. So when we got into orbit around Bennu on slide 9, I just wanted to put the Bennu's size in a bit of context with the other small bodies that have been orbited before. And we got a world record. The reason why the world record for this was available after the Hayabusa mission is that the entire Hayabusa mission was executed without ever going into orbit around Itokawa. So actually orbiting Bennu was a new achievement for an asteroid of this size class. And I also wanted to point out something that about these small body orbits, which is everything around these small bodies, because the gravity is very low, everything can move very slowly. So right now we're in a 21-hour orbit around Bennu, getting ready for TAG. And the length of that orbit, is kind of similar to if you were running a 5K. So if you can cover the distance in a 5K in less than 21 hours, then you can definitely move faster than OSIRIS-REx is moving at this very moment relative to Bennu. So next slide. So Bennu had a few surprises for us. So our first surprise was the sheer number of boulders on Bennu. So from the radar data, we had a really good idea that there was at least one very large boulder on Bennu that showed up, nice and clear in the radar data. We knew that one boulder was there. We didn't know that there were going to be boulders everywhere and that boulders would be like the main type of surface that was all over this asteroid. This was kind of a two-edged discovery for us. On the one hand, scientifically, these boulders are fantastic. And they're super interesting. It's great to see so much detail on them, and every one of them is telling us a little piece of the history of Bennu. And on the next slide, you can see some of the detail and texture that we're able to see from these boulders. And they're really weird. We think that they're not as strong and well consolidated as you would expect a boulder of this size to be on the Earth. Partly because when you look at them thermally, instead of looking like a big solid rock, they actually look like more of a pile of sand or gravel. So that means that they're probably low in density and low in thermal conductivity. So there's probably a lot of pore space and fractures, inside these boulders, interrupting those thermal conductivity paths in order to produce that effect. But, we're not 100% certain. That's just our best guess right now about like what's causing that really low thermal conductivity. And then these textures, they look kind of crumbly. A lot of places you can see them. They almost look like they're disintegrating in front of your eyes. Like you can see cracks. You can see pieces of boulders next to each other that look like they used to be part of the same boulder. So we think there's a lot of kind of poorly consolidated material here that still manages to stick together for a certain amount of time in these large boulders, and it's really interesting. But on the other hand, the discovery of all these large boulders did greatly complicate our plans for collecting a sample from the surface of Bennu, because we would like to do that without hitting a boulder with our spacecraft at any point. So in Ben's talk, he's going to elaborate a lot more on all the adaptations and clever ways around that we had to come up with on the mission in order to avoid crashing into a boulder on the way to our sample. Okay, next slide, slide 12, I think. So we were able to confirm that all these boulders did contain the hydrated and organic rich material that we kind of came there looking for, which is terrific. So one of our spectrometers is named OSIRIS, and it was built right here at NASA Goddard. And so the figure shows some data from OSIRIS showing a nice, robust hydration feature, right where we were hoping to see it, which is terrific. This feature is very widespread, and we see it all over the asteroid. It's clearly the main material on the asteroid. So we were pretty excited to see that. Slide 13 shows a little bit, a cartoon diagram about how hydrothermal alteration happens. So your high temperature nebular condensates come together and they accrete with a bunch of ice, and then you have just enough heat to melt the ice and increase the reaction rate so that all those mineral water reactions happen, and you end up with like clay minerals and phyllosilicates, like we were talking about, in which the water molecules get incorporated into the structure of the rock. But it has to be enough heat for that to happen, and not so much heat that the water just gets vaporized and goes away. So these are some pretty important constraints on the conditions in the early solar system under which these rocks were made. Slide 14, surprise number 2. Bennu is spitting particles out into space. So every so often, and we were not expecting to see this at all, like on approach, we did a whole particle natural satellite search looking for spacecraft hazards. We didn't see anything, but that search was focused on particles that would be of a size hazardous to the spacecraft, about 10 centimeters or so. And most of these particles, and so once we get into orbit, and then we saw this happening, but most of these particles are smaller than 10 centimeters. So that explains why we didn't see them on approach. But yeah, there are, little pieces of pebbles or gravel are just getting, ejected at a few centimeters per second into space every so often, but in these events from Bennu. And we've tracked, slide 15, we've been able to track hundreds of them by now. And, watch where they go. Most of them eventually just fall back onto the surface of Bennu. Some of them get ejected, kind of blown away by the solar wind. So they don't stay in stable orbits for a terribly long time on the whole. But watching them move around has definitely helped us out with getting a better gravity field from Bennu. Slide 16 lists some of the hypotheses that we have for where these particle ejection events are coming from. So right now, the leading hypotheses are meteorite impacts or thermal stress fracturing, in which the rock just undergoes a stress fracture, and that's actually a fairly energetic event compared to the gravity of Bennu. And then so the particles from that can just kind of go flying. But we don't know for sure. This is definitely an area of active research here. All right, slide 17 shows surprise number 3, xenoliths. So xenoliths are rocks that we're pretty sure came from somewhere else. And why do we say that? So this is hot off the presses. This is Della Justina and Kaplan just published this. And so yeah, almost all of Bennu is covered with these dark, crumbly looking rocks. But once in a while, you see a bright rock sticking out like a sore thumb. And when we looked at these spectrally, they didn't look like the rest of Bennu at all. In fact, they looked like basalts, which is a volcanic rock. Now, why would there be a volcanic rock on Bennu? Like, Bennu does not have a volcano on it. It is too small to generate that kind of heat inside, or accumulate the kind of heat inside that would produce actual volcanic activity. So we think these rocks really had to originate somewhere else. And what they really look like on slide 18, when you think about basalts in the asteroid belt, especially in the inner asteroid belt, they mostly come from one place, which is this fantastic, weird, wonderful asteroid for Vesta, which was one of the targets of the Dawn mission a few years back. And Vesta is absolutely covered with basalts. It's kind of like the moon that way, covered with igneous rocks, except with Vesta, instead of basalts and anorthosites, it's like basalts and more basalts. And Vesta has an asteroid family that was created by one of these impacts that flung out little basaltic bits of Vesta, throughout this whole area, shown by the box here in the inner main asteroid belt. So somehow, this Vesta material, we think, has to have landed on the surface of Bennu or Bennu's parent body back when it was living in the main belt. And why why chunks of Vesta and not chunks of any of this other stuff in the inner main belt? Because most of the stuff in the inner main belt is not actually pieces of Vesta. We're still thinking about that, but I think it's telling us something important about the history of Bennu and its parent body in the deep past, which is pretty exciting. All right, slide 19. Where are we going tomorrow? So we looked all over the asteroid, and this is the largest area on the asteroid where we thought that there would be sampleable material. It looks great, except that it has giant boulders next to it, because every single thing on Bennu has giant boulders next to it. But it sure looks like there's sampleable material here, and Ben will go into a little bit more detail on that, I think. So slide 20 just puts the site in context of the size of the sampler head. Slide 21 has a little animation here showing the sampler head in rehearsal, so not quite in action, but almost in action, like during one of the rehearsals with the asteroid in the background, which is a very dramatic shot. So the sampler head is sitting at the end of its arm, and like maybe we should go straight to slide 23. So here's the head during one of the ground tests. And so what happens is that the head makes contact with the asteroid material. There are gas bottles mounted up on the arm that are going to inject nitrogen into the surface of the asteroid and stir up the loose material, pebbles and gravel, which will flow into the head through a one-way modular flap valve and get caught in the ring-shaped sample chamber, which has a filter around the outside. And then slide 24 shows a person for a scale, so you can see how big this whole thing is really easily. And the gas bottles you can see mounted kind of halfway down the last arm segment over there. And then just to wrap up, slide 25 should be showing you a video of how the TAG event is going to work. So this spacecraft's going to approach nice and slow, make contact with the surface, discharge the gas bottles, remain in contact with the surface for just 5 seconds, and then fire the rockets and get out of the plume of material coming back up from the surface. Then once we're sure that there is material inside the TAG SAM head, we're going to stow it in the sample return capsule, which is equipped with a nice heat shield and parachute system to keep the samples safe on their way back through the Earth's atmosphere. And that's what I've got. The last slide says discussion, but we're going to hold the discussion until after Ben's talk. So Ben, over to you, I think.
Yep, thank you, Dr. Lim. And now we'll hear from Dr. Ashman.
Great. So Dr. Lim gave us a really excellent overview of the mission and why OSIRIS-REx is at Bennu and what we hope to learn from retrieving a sample and bringing it back here to Earth. I hope to talk in the next few slides about how we're executing this mission, in particular from a flight dynamics and navigation perspective. So if you advance to the next slide, this is our first really good look at Bennu. It's a series of polycam images taken shortly after arrival back in December of 2018, about a 0.5 meter per pixel resolution. And the first thing you notice may be that very large boulder in the southern hemisphere that we call Ben. At almost 100 feet tall, this boulder was perceptible in ground-based observations before we even began our journey. But the thing that really struck the mission team was the sheer abundance of meter-scale boulders all over the surface of that asteroid. In fact, there are boulders that are tens of meters in size. And the absence of clear, safe landing areas. Now, if you advance to the next slide and start the animation, after a lengthy search, the project settled on a site that we call Nightingale. Lucy showed some pictures of that already, but I really like this visualization that shows topography from the laser altimeter overlaid with high resolution and orbital imagery. And despite the presence of some very large hazards, such as the daunting Mount Doom that you can see, that tallest boulder, about 20 feet tall, this impact crater in the high northern latitudes represents a relatively clear, safe region of sampleable material. And when I say relative, I mean relative to the rest of the asteroid. So if you go to the next slide, I'll put that in context by saying, prior to seeing Bennu, we really expected it to look like other asteroids that spacecraft have visited. Lucy showed a couple of those. We anticipated large regions of sandy, benign terrain, but the original navigation requirement of bringing the spacecraft to within 25 meters of the target sample site is clearly inadequate. If you overlay the 50-meter diameter circle on this image of Nightingale, you can see even the Mount Doom boulder is within the limits of that circle. So over the entire asteroid, we were unable to find any areas of this size that were clear and hazard-free. Nature leveraged a more stringent requirement that we bring the spacecraft to within 8 meters of the target sample site. This is only 10% of the original area. For this reason and others, high precision navigation is essential to the OSIRIS-REx science. Navigation is always important for achieving mission science objectives, but it's exciting to work on a mission like this, where both science and navigation are so closely intertwined. In the following slides, I want to describe how we've navigated around Bennu up to this point and why we're confident that we can safely bring the spacecraft down to within this 16-meter diameter tag target. Go ahead to the next slide. I can't talk about OSIRIS-REx without sharing one of my favorite pictures from the mission. We launched in September 2016, and a year later, in September 2017, flew past the Earth using its gravity to change the inclination of the spacecraft's orbit to match the orbital plane of Bennu. Lucy showed how the orbit of Bennu is pretty similar to the orbit of Earth in terms of distance from the sun, but it's inclined about 6 degrees. And during this flyby, OSIRIS-REx took this picture where you can see the Earth in the top left, and then way down there in the bottom right in the same frame, the Earth's moon. I think this is a striking reminder of the vast emptiness of space. If you go to the next slide, after traveling 1.8 billion kilometers, we finally got our first glimpse of the asteroid. We're still 2.2 million kilometers away at the time this series of polycam images were taken back in August of 2018. But it was very exciting to see that subpixel smudge of light moving against the background field of stars. Go ahead to the next slide, slide 6. Over the following days, weeks, and months, as we approached Bennu, it became increasingly resolved in imagery. We were able to refine that shape model estimate that we had before launch from ground-based observations and begin determining surface features. The sequence of images at the right have overlaid on it a red outline of the asteroid based on our shape model. Both the shape model and the details of these surface features are essential to navigating around the asteroid at this size. And unfortunately, I can't tell if you've gotten to the end of that animation, but at the very end, you start to see some details of the surface features. Okay, why is the shape and the details of these surface features so important to navigation? Go ahead to slide 7. During outbound cruise, the radio links with the Deep Space Network provide us with range, Doppler, and delta differenced one-way range. Delta Dor is another measurement using the Deep Space Network that uses measurements from 2 stations widely distributed across the surface of the Earth, providing us some visibility into the dimensions that aren't along the line of sight. A combination of these radio measurements allow us to estimate where the spacecraft is to within kilometers, and during outbound cruise, that's perfectly sufficient. But when you get to Bennu, the asteroid itself is only, well, it's less than half a kilometer in diameter, and that's where we need to use optical navigation to navigate at the precision required. Go ahead to the next slide. We've got 3 kinds of optical navigation that are used in this mission. The first is star-based OpNav, where we take a long exposure image and extract stars from that image. And by comparing those to a star catalog, we can get an estimate of what direction the spacecraft is pointing relative to that fixed celestial sphere. The second kind of OpNav involves using the shape model of the asteroid and finding the horizon of the asteroid in imagery, what's called the limb. By finding the limb and knowing something about the shape and its rotation at the time the picture was taken, you can estimate where the center of the body is. This provides us with a bearing measurement from where the spacecraft is to where the asteroid is relative to that inertial frame, those stars in the background. And finally, when you get close enough to Bennu that you can start to make out surface features, we're able to produce high resolution maps of the asteroid and then begin navigating relative to known landmarks on the surface. And this is what really allows us to navigate as accurately as we need to for this mission. If you go to the next slide, there's a special version of landmark navigation that's used during TAG. TAG was never supposed to have navigation images. It was supposed to be all LiDAR based because we expected large, hazard-free regions that we could land in. And analysis before launch suggested using just the LiDAR, we were exceeding our 50-meter diameter target by as much as 20%. As we saw, the area of the target that we now have to hit is only 10% of that original area. And so we had to fall back to this backup technique. It's very similar to the landmark navigation I just mentioned before, but natural feature tracking is performed on board. At about 2 astronomical units, it takes 18.5 minutes for a signal from OSIRIS-REx to reach us here on Earth. And during the TAG activity tomorrow, the maneuvers are as close as 20 minutes from each other. So there simply isn't enough time for the ground to be in the loop in terms of navigating down to the surface. And so OSIRIS-REx has loaded on board a subset of those landmarks that we use for navigation and is able to autonomously perform an updated estimate of where the spacecraft is and perform real-time adjustments to the maneuvers that bring us down to the surface. As an additional benefit, we're able to autonomously wave off if the estimated touchdown point is found to be intersecting with some hazard on the surface. It's just one example of the really significant improvements that we had to make to our ability to navigate during TAG because of that unexpectedly rugged surface. Go ahead to the next slide, I believe slide 10. With the exception of NFT, navigation involves processing those measurements, the images and the radio measurements from the Deep Space Network, and performing orbit determination here on the ground. Orbit determination, or OD, is a blanket term for estimating the position of the spacecraft over time, what we call a trajectory. The steps are basically perform those observations, for example, the DSN radio links and imagery, then estimate the spacecraft position and velocity, what we call the state of the spacecraft. We estimate this at some time and use these measurements, the measurements and a priori current estimate of our state. Finally, we propagate that spacecraft state forward in time using knowledge of orbital mechanics and flight dynamics, as well as the perturbing forces involved. Uncertainty in the spacecraft state increases with time since you last processed measurements. And when that uncertainty exceeds an acceptable level, then you need to perform an updated OD here on the ground and send it up to the spacecraft. What constitutes an acceptable level really depends what you are doing with the spacecraft. You may be performing science observations that enforce very stringent requirements on how precisely you know where you are. But at minimum, you need to navigate accurately enough to keep Bennu in the field of view of those cameras so we can continue making those optical navigation measurements. You may be maneuvering. So maneuvering the spacecraft typically requires an update before thrusters are fired, and then another afterward in order to reconstruct the burn. Go ahead to the next slide. The uncertainty in your state and its evolution over time, the rate at which that uncertainty grows, is a combination of measurement errors and errors in the propagation force modeling. Measurement errors for optical navigation depend on how accurately you've modeled the shape of the asteroid and the locations of your landmarks, as well as camera modeling, pointing, and the influences of thermal noise that affects the radio link with the Deep Space Network as well. And then propagation force modeling is kind of a unique problem in cases like this small body navigation. I've shown a plot there at the right where you can see over time along the x-axis the magnitudes of the different perturbing forces that we need to consider in order to accurately project the spacecraft forward. And the dominant force there is Bennu's gravity model. It's pretty apparent just from seeing a picture of Bennu that this is a non-uniform body, both in terms of its shape and its density. So the details of the gravity field are really important. But comparable in magnitude is the solar radiation pressure, that is the force from photons hitting the spacecraft from the sun. And because of Bennu's small size, it has about 3/millionths the gravity that we have here on Earth. This is comparable to the gravity experienced by astronauts on the International Space Station, something we typically refer to as 0G. So you can imagine how small the gravity is here around Bennu. Solar radiation pressure depends on the orientation of the spacecraft and the material properties, and if you look at that red line, it's a pretty significant factor here. It's also important to accurately model the thermal re-radiation both of the spacecraft as well as the asteroid itself, and forces from even using your antennas to emit energy and transmit data. Finally, it's very important to model the maneuvers accurately. So we've got several different thruster sets that are used on the spacecraft, and depending on the magnitude of the maneuver, and being able to model those maneuvers accurately allows you to design the maneuvers as well as reconstruct the trajectory after you've performed a maneuver. Go ahead to the next slide. This shows a timeline of proximity operations. Proximity operations encompasses all of the activities that we performed since arriving at Bennu back in December 2018. Broadly, it can be divided into the navigation, site selection, and sample acquisition campaigns. In practice, this means we've alternated between periods of being in orbit around the asteroid and performing these arcing flyovers designed to gather science observations. The schedule shown here was modified to account for several surprises. First, we added additional time in orbit to observe the particles that Lucy mentioned Bennu is emitting. Definitely a surprise when we got there to discover that Bennu is an active asteroid. We also performed a much more detailed site characterization campaign, down selecting from the sort of site finalists to finally arrive at Nightingale as our prime target because of how rugged the surface is, and that was really significant. A significant effort. On top of all this, we actually delayed TAG to account for risks due to the COVID-19 pandemic. And so the team's really risen to the challenge and overcome quite a bit in bringing us to this point where we are today. Go ahead to the next slide. This shows the beginning of the navigation campaign. So we first get to the asteroid, and our objective initially is to perform a series of 7-kilometer distance flybys, 4 of them, 2 over the North Pole, 1 over the equator, and then the South Pole, in order to determine Bennu's mass. This was to reduce our uncertainty in the gravitational parameter of Bennu. And if you go ahead to the next slide and click on the inset there to start the animation, second part of the navigation campaign was, after refining our understanding of Bennu's gravity, we captured into a frozen terminator plane orbit. This is an orbit above the day-night line where the orbital eccentricity is tailored to balance perturbations due to solar radiation pressure and minimize changes in the orbital elements over the life of the orbit. As Lucy mentioned, Orbit A set a world record, first for the smallest object ever orbited, but then also for the smallest orbit ever executed. At the time, I think it was about 1 kilometer semi-major axis, but our subsequent orbits have been even smaller, so we broke our own records there. Go ahead to the next slide and click the inset to start the animation. With the navigation campaign complete, the science campaign began in earnest. This is last spring in 2019 with the detailed survey phase. For flight dynamics, this meant maneuvering the spacecraft 42 times. The animation here only shows some of the 3 to 5 kilometer flyovers that were designed to enable science observations of the entire surface of Bennu at a wide variety of viewing geometries and local times. Further observations were taken during subsequent orbital phases and flyovers of the candidate sample sites, culminating in the selection of Nightingale as the primary target for sample collection. Go ahead then to the next slide, slide 15. Oh, wait, 16. After selecting Nightingale as the primary tag site, we began a series of rehearsals of the tag activity. Similar to the tag event that'll happen tomorrow, this involved a series of maneuvers. First, to depart the Terminator plane orbit, flying up over the night side of the asteroid into the northern hemisphere. Then a maneuver that we call the checkpoint maneuver that matches the rotation rate of Bennu, followed by the match point maneuver that eliminates all of the lateral velocity and brings us into that descent trajectory, descending down at about 10 centimeters per second, or some people like to say the speed of a beetle running across the ground. During the rehearsals, we didn't go all the way to the surface. So in April 2020, we performed the checkpoint rehearsal. So after that second burn, the checkpoint burn, we reached an altitude of about 65 meters above the surface and then backed away. And then in August, just a couple months ago, we performed the match point rehearsal, descending to about 40 meters above the asteroid and then backing away. Actually, if you go to the next slide, an animation should play showing a series of NavCam2 images collected during the match point rehearsal. These rehearsals exercised that autonomous onboard optical navigation technique, the natural feature tracking. You can see us slewing around into an attitude to view those different landmarks, and then gradually approaching the sample site from the southeast, flying just over Mount Doom down to that 40 meter or so altitude. I want to highlight just how rugged the surface of Bennu is. You can just see it's boulders everywhere, and in response to that, we've actually mapped Bennu surface in greater detail than any other body in our solar system, including the Earth and our moon. I think we're at about less than 2 centimeters resolution. And this is it's been an incredible feat by the entire team to respond to the unexpected number of large-scale boulders and absence of clear landing sites. Go ahead then to the next slide. I think that's slide 17. So throughout this mission, we've designed and executed more than 110 maneuvers and delivered more than 290 trajectory solutions. We're achieving meter-level trajectory prediction accuracy during orbital phases over a few days. The plot at right illuminates this a little bit. Along the y-axis, you can see the days since measurements were last processed and how the uncertainty shown in that sort of pink background is increasing over time. Overlaid on top of that are a large number of trajectory solutions, and so you can see how those are actually performing. Go ahead into the next slide. I see we're getting up to the time limit here, but tag target, as I've said, I think the tag target is an order of magnitude, well, I should say it's 10% the area of the anticipated target that we were aiming to hit. So all subsystems had to exceed the original requirements in order to achieve this goal. In particular, the navigation and flight dynamics team was able to model Bennu's gravity field in great detail, aided by observing the particle trajectories. We have a ray trace solar radiation pressure model and thermal modeling that takes into account all the changes in the spacecraft attitude. We've precisely characterized Bennu's rotation, orientation, and albedo and achieved centimeter scale accuracy in the shape model and landmark locations. Nearly all of those 110 maneuvers have performed within 1 sigma of the design. And as I've discussed, we performed an overhaul of tag navigation to make natural feature tracking prime. My final slide then is just an animation of the tag activity that will happen tomorrow. And you can play that. I don't know if you need to cut me off, but It's very similar to the rehearsals that I just discussed, and Lucy did talk about some of the details there about during that final touchdown, where we spend about 5 seconds on the surface, fire the nitrogen canisters, and hopefully churn up some fine-grained regolith into the TAG SAM collector head before backing away. We'll spend the next few days after that reconstructing our trajectory to see where we actually touch the surface and assessing whether we've collected the 60 grams of sample that are necessary for the minimum success criteria. I hope you'll follow along at asteroidmission.org tomorrow, or if you go to nasa.gov/live, I think events start at about 5:30 Eastern. Thank you.
Thank you both so much for those great presentations. We do have a few questions that have come in, a couple that were submitted ahead of time, as well as some that have come in since we got started today. And so, Ben, I'm actually going to kick the first one over to you. So you talked about many of the challenges that the team has had to overcome, but what has been the most challenging aspect, in your opinion?
Okay, well, I don't want to get into the details, but you can imagine how if you have some uncertainty in your orbit, the parameters of your orbit, but you also have uncertainty in the size and mass of the asteroid, that those uncertainties are actually very difficult to entangle. So the navigation team's gotten very creative with using the measurements, both images and processing images taken at different times in different orbital phases, and combining them together, as well as using altimetry data to disentangle some of those highly correlated uncertainties. And that's really been one of the big challenges.
Great, thank you. Lucy, are there any concerns about the sample deteriorating on the return trip? For example, with the high G's or vibration that it's going to experience during reentry?
Yeah, I mean, we realize that you know, something that's a pebble when it enters the TAG SAM head, it could get disaggregated, as you say, by any vibration or any forces. That's just something that, yeah, we're prepared for. We are going to SEMLink to protect the sample against heating. So the mission is designed so that nothing will be heated above, I think, 75 Celsius was the requirement, based on, you know, chemically when we would start to lose things that we cared about. But the vibration reentry forces, that's, you know, just something that we can't do a lot about.
Thank you. Ben, let's see. How do you plan to actually maintain contact with the asteroid for 5 seconds or so? And how did you convince yourself that this method would work?
The contact is actually basically after that match point burn, the spacecraft descends down to the surface, and it's just that very small amount of momentum that brings us into contact and presses down on the surface. It is going to be very interesting. One of the only thing we haven't done in rehearsals is see what happens when we actually touch the surface of Bennu, and there's maybe some variability there, but the time of touching the surface is really determined by when we do that back away burn. So we'll back away after after that 5 seconds of contact with the surface. And yeah, I guess that's my answer.
Great, thank you. Let's see. Lucy, can you study the debris that is knocked off the surface by TAG?
We're going to do our best. We're going to keep imaging during the backaway burn, and we sure are interested in looking at the particle sizes of the debris that gets kicked up. And whether there's any other type of motion that we can detect on the surface, besides, under things moving laterally, for example. So, I'm really looking forward to that data set.
Great. Let's see, we have another question that I think is for both of you. So, what were the top driving requirements in selecting Nightingale from both the science team and the spacecraft ops team? So Ben, I'll let you start.
Okay, well, from the navigation perspective, I think we were most concerned with safety and deliverability. Sampleability, okay, so then there's sampleability and science value, which I'll leave maybe those last two for Lucy. But in terms of deliverability and safety, we really had to find a spot that had a minimum number of large hazards within that target area. We were looking for the largest area in which we thought we could safely bring the spacecraft to the surface and back away. But as I pointed out, we were really limited in how big a clear area that we could find. So all 4 of the final candidates were impact craters that cleared a small amount of area, but we were really driven, and I think that was probably the big driving factor in choosing the sample site. Early on in the mission, we believed that science value would be a primary driver, but getting the spacecraft in and out safely was really important.
Yeah, I would agree with that. And then the sampleability was the main place where the science team had contact with the sample selection process. So that's the, you know, the presence of material that will fit in the TAGSAM head and be, and you know, which, you know, it's got kind of a 2 centimeter limit on what will fit, you know, fit through that valve, the Mylar valve, and actually be captured in the head. We actually, the science team hired a whole bunch of people to just count rocks. So you can see maps. We have maps of these sample sites with pretty much every single rock that, you know, pebble that can be identified in those images, counted and measured. And so you know, that's, I'm sure somebody's thesis is going to be written on that data too one of these days. But it was a huge effort to actually do all that counting. And Nightingale definitely came out ahead on the sampleability stakes. Yeah, what Ben said, like early on in the mission, we thought that there would be, you know, great distinctions in science value between one site and another. You know, we thought we would be looking for things that had experienced less space weathering or were more water or organics rich or something like that from one part of the asteroid to another. But, you know, I think the science value is going to be pretty high everywhere on this asteroid. You know, spectrally, it's, you know, it's so consistent from one site to another. The differences are pretty minor. So I think we were actually, that was kind of a relief to us that like the science value was going to be very high everywhere. And so we could prioritize like the probability of success in other dimensions.
If I could, I want to add one comment related to that. I think it's important to remember there's small scale variability at the sample site that could affect our ability to collect enough sample tomorrow, even if we bring ourselves to within that tag target that I was talking about with the 16-meter diameter. And so the team is prepared for doing other attempts if we don't collect a sufficient amount of sample tomorrow. And there's just that possibility that you land the TAGSAM head on maybe a small rock that causes you to have some difficulty getting enough sample, and that's all part of the plan. We're prepared for that kind of eventuality.
Yeah, we have 3 gas bottles on there, so even if we fully discharge one of them, we have 2 more attempts that include blowing the gas bottles, and they're built into the schedule as well.
Great, thank you. And I do have one final question that's related to the tag attempt tomorrow. So if a boulder is hit during the attempt, will a sample be taken? Is there a way to do that? And you did mention that there is a plan B to make other attempts as well. But that boulder question I thought was interesting.
Yeah, you can, if you want to talk about the sampleability, Lucy.
Well, it depends on like what they mean by hitting a boulder, like hitting a boulder with a TAGSAM head or with some other part of the spacecraft. There's an abort criterion. So if the spacecraft will keep imaging during descent, and then if it detects that, you know, it's out of bounds on the hazard avoidance, like then it will abort. So it won't.
That was one of the, I guess, really important things with NFT, that we were able to switch over to having that autonomous navigation process that allows us to wave off if there's any chance of the spacecraft intersecting with a hazard.
Well, fingers crossed that everything is going to go well tomorrow, and you'll get the full sample that you're hoping for, and then we'll be able to get some amazing data when it's returned to Earth, as well as really cool images, is my understanding, coming down hopefully later this week. So I know that we all are wishing the team the best, and you guys have done an amazing job throughout the mission. You guys have done an amazing job with the presentation today. And so I just want to thank you and thank everyone who tuned in today. Also, just real quick, for those of you watching, if you have family and friends who are interested in learning more about the mission and hopefully again seeing some images from TAG, we are hosting the second installment of a new public engagement event, virtual event that Goddard is hosting called Getting to Know Goddard, and it will focus on OSIRIS-REx, and that will take place next Tuesday, the 27th. And so I think Travis is going to post a slide about that with more information as we close out. But again, thank you to our presenters. Thank you everyone for tuning in today, and good luck OSIRIS-REx. Thanks.
Thank you so much.
Yeah, thanks for having me.